So I want to go over just a few things not related to content here, just to begin with. On your desk is assignment number 1, and I'll get to that in a minute. With all these short weeks, I mean, you have a 4-day weekend after today. Next week, we only have a 4-day week because on the Friday is a PD day, and then you have another 4-day weekend attached to that PD day because Monday is family day. So then we have another 4-day week. The way the schedule works out is if we followed my schedule for the course, we would end up writing our Unit 1 exam the day after Family Day, which is really not ideal. Part of me wants to say it shouldn't matter, but the other part of me is realistic, knowing that students are going to go home for a 4-day weekend and not worry too much about school. So what I've decided to do is, what we're going to do today is get started on Chapter 2, and we're going to do 2.1. Then we have Teachers' Convention. You got a 4-day weekend. We're going to come back on Monday. We're going to be doing 2.2. 2.3, which is the final lesson in this first unit, we're not going to do in this unit, which means the couple or 3 questions related to 2.3 that would be on the unit exam are not going to be on the unit exam. And then that will give us my regular 2 days of review. I like to have 2 days for each unit review to get lots of practice. And then we'll write our exam before the long weekend. Then when we get back after that second long weekend in February, second extra long weekend, we will do 2.3. And then the next day we'll get started with Unit 2, which is Chapter 3. Okay. I haven't decided whether I'm going to evaluate you on 2.3 in the next unit exam, or maybe just an assignment or a quiz. I don't know. Because quite frankly, 2.3 is just this tiny little sliver of the curriculum. It's not crucial. I mean, it's important that you know it, but it doesn't form a big foundation for anything. Okay, on your desk is a written response assignment. That's your first written response question or problem set that's due on the Tuesday of next week. Written responses need to be completed in an organized way, in a clear way, and you need to follow the directing words. Directing words are those words that are given in bold. So if it says identify, you identify. If it says explain, you need to explain. And explaining, some students still struggle with this even at the grade 12 level. Explaining is not a description of what you did. Explaining is a description of what you did coupled with why you did what you did. So if, for example, I ask you to explain why, and this isn't on this question, but if I ask you to explain why, if the x-intercept of a function is 5, why is the y-intercept of the inverse 5? Simply saying all of the properties of x on the function become all of the properties of y is not an explanation. That's a statement of how you came up with the answer. A better explanation would be for you to say something like the mapping when you go from a function to an inverse is x comma y maps to y comma x. So the x-intercept of 5 comma 0 maps to 0 comma 5, and 0 comma 5 is a y-intercept. There's more involved. And I really don't want anybody to write essays here. There's a fine balance between giving enough information that you're following the rules of the written response by explaining and describing things properly, and just going on and on and on and being what we call verbose, saying too much. Okay. Written response questions in this course will always contain 2 parts, A and B. In this case, I've got bullets for them. One of the parts will be 2 marks. One of the parts will be 3 marks. When you write your diploma exam at the end of the semester, you will have 3 written responses, forming 25% of your mark on the diploma exam. When you write unit exams, and you should be familiar with this from Math 20, you have 1 written response worth 25%. And I realize that that's a fairly heavy load for one question. But the difference between the written response on my exams and the diploma exams is the written response on my exams it's more all-encompassing of the whole unit. It will cover more material than maybe the written response will on the diploma exam. And as we get deeper into the course, you'll see lots of examples of diploma exam written response questions. Okay? The written response questions that I give you as assignments are important that you complete for your marks, but they're also important so that you get feedback and know what to expect on a diploma exam. You know, I want you walking into that diploma exam and reading a written response question and knowing what those markers are thinking when they look at your work, what they're expecting to see. That's all the clerical stuff. Let's get going with going over problems from yesterday. This deals with inverses of functions. I think the lesson was on page 27 of your handout. But this is from yesterday's lesson. There's a variety of questions dealing with inverses of functions. We'll start off with a review of what we learned. To begin with, just looking at the first statement at the top of the screen here. An inverse of a function is found by interchanging or switching all of the x and y coordinates of every point. And I think that doesn't really require a lot of explanation. We're just saying that, for example, we can pick a point here. I can pick this point on the original function. The coordinates of that point on the original function are x equals 2 and y equals 4. Well, when you swap those points, x equals 4 and y equals 2. So not swap the points, swap the coordinates. When you swap the coordinates, that's what happens. And we discovered yesterday, because of that, we can write the mapping as x comma y maps to y comma x. We discovered, just by way of an example, that it turns out that that dotted kind of greenish line, which is y equals x, is a line of reflection between a function and its inverse. I wouldn't recommend, if you were ever asked on a written response, and sometimes you might be, I wouldn't recommend drawing an inverse by trying to reflect the function. Unless you're that kind of visual person in your brain, I can't wrap my head around it, and most students can't either. I think it's better to pick points, swap the x and y values, and replot them. Then you can see, well, yeah, it's a nice reflection. This is very important. When it comes to written response, this might require more explanation. But if you're given a problem, a multiple choice or a numerical response problem, you can make use of that very easily without having to justify it. Again, if an x-intercept of a function is 5, that means the y-intercept of the inverse is going to be 5. If the domain of a function is any real number, the range of the inverse will be any real number, because whatever x was doing on the original, y does on the inverse. And whatever y was doing on the original, x does on the inverse. To determine the equation of an inverse, and this is definitely something you could see on a written response, you take the equation of the original function and you switch x and y, and then algebraically you rearrange that result for y. In order to decide if the inverse of a function is a function itself, what I mean by that is in order to decide if the pink graph happens to be an inverse, because when you take the inverse of a function, it may or may not give you an inverse. You use the vertical line test. We said yesterday that if I gave you the blue graph, all right, and I said, is the inverse of the blue graph a function? One of the things you could do is you could take all the points on the blue graph, swap x and y, and replot them, and then look at the resulting inverse, which is the pink graph, and say, well, it fails the vertical line test. You could do that. But you don't have to do that to know that the inverse of the blue graph is not a function. If the blue graph goes up and down, then the inverse has to go back and forth. Up and down is a y kind of description. So it goes from big Y's to small y's back to big Y's. If I switch x and y, it's going to go from big X's to small x's back to big X's. It's going to fail the vertical line test. And that's why your textbook talks about the horizontal line test for the original function. I've got at the bottom some examples, some specific examples in terms of words, of functions whose inverses would not be functions, and they are absolute value functions because they go up and down, that's what they look like, and parabolas or quadratic functions because they go up and down. But I think it's more important for you to understand that any function that goes up and down will have an inverse that is not a function. That takes us to domain restrictions. So if I take a look at that blue graph, and these pages will be in a review handout that you end up getting. Okay. When I take a look at the equation of the blue function, it's y equals x plus 3 quantity squared minus 7. If you write that and you switch x and y and rearrange it, trust me, you're going to get the equation of the red graph, which is at the bottom of the screen. You're going to get y equals negative 3 plus or minus root x plus 7, or plus or minus root x plus 7 minus 3. And it's that plus or minus that makes this red thing not a function, because the plus part is the curve at the top, and the minus part is the curve below. So if you were ever asked for a domain restriction on an original graph, so the inverse is a function, you have to, in this case where there's a parabola, you have to use your ability, because you're given permission to do this in this question. Use that permission to erase 1/2 of the original parabola. So this is saying if you were allowed to, how could we restrict the domain of the blue function? And the key for parabolas anyway is the value of h. It's where the vertex is horizontally. If that has an h value of negative 3, that means the vertex is over here at negative 3. So if I get rid of the right side and keep the left side, the right side is responsible for the top of this red graph. The top would disappear if I got rid of the right. And in fact, I'm going to show these to you right here. If the restriction on the blue graph, which actually went all the way over to here, was x is less than or equal to negative 3, then we would only keep the left side, and we would only get a bottom half for the inverse. So x is less than or equal to negative 3 is a restriction, and x is greater than or equal to negative 3 would be a restriction. I mean, that's a useful thing to remember for parabolas, which are quadratic functions, or the v's, which are absolute value functions. But the bottom line is you restrict the domain so the graph of the original only goes up or only goes down. All right, does anybody have any questions you would like me to go over here? Go ahead.
Question 15.
15? Okay. Okay, so given that function, determine each of the following. So I'm going to walk away from number 15 just for a second, Lynette. If I gave you f of x equals negative 3x plus 2, and I said, what is f of 1? What that means, that's a language we use in math, kind of a code. It means go ahead and put 1 in for x in f, right? And I can see you looking back and forth here. Don't worry about that just yet, okay? So what that means is I find the function f, and it's right here, and I replace every x in the function with 1, and I get negative 3 times 1 plus 2, and that works out to negative 1. But what it works out to is not my point. In fact, I'm just going to get rid of that. It's equal to whatever that works out to. If I said to you, what is g of 1, well, you would need to find the function that is g of x, wouldn't you? So you'd look around and maybe someplace in the question you would see, oh, g of x equals 1 plus x. And if that was what g of x was, then what you would do is you would go 1 plus this 1 that you're putting in. If I said to you, what is f of, and I chose 1 for a reason, what is f of 4? Then you would look for f of x, and you would put a 4 in for x, wouldn't you? And if I said, what is g of 4? You would put a 4 in for x. Okay. If I say, what is this? I need to put 4 into this function. I need to find the function, the inverse of f of x, so that I can put 4 in for x in that. Well, how are we going to do that? This is the original function. I haven't done anything to it by writing y equals 4x minus 2. I've just changed the f of x to y. And now what I'm going to do is write the inverse of the function by writing x equals 4y minus 2. And I can rearrange this for y, add 2 to both sides, divide everything by 4, and I'm the kind of guy that likes just separate terms. You could certainly write everybody x plus 2 all over 4. But I like to say x over 4, which is a quarter x, plus 2 over 4, which is a half. And because, Lynette and everyone, y is equal to a linear expression, it is a function. It would pass the vertical line test. And that means that this 1/4 x plus 1/2 could be written as this. And I know I resist the temptation to say f to the negative 1 of x. It's technically, that's what you can say. But then it sounds like an exponent, and that's not what it is. It's the inverse of f of x. So I would write this, but say the inverse of f of x. And that means if you want to find the inverse of f of x at 4, you put 4 in here for x. Does that make sense? Okay. Incidentally, I run the risk here of maybe confusing some people with this, but I think it's going to be helpful for many of you. You don't have to do all of this. What you could do is say, x is an input on the original function, and I want to find out what the y coordinate is. So you could say, I'm going to put this in as a y coordinate and solve for x on the original. And that idea is going to be helpful later on when we have logarithmic and exponential functions, which are inverses. And going from one to the other is a lot of work. Anyway, is that okay? All right. Any other questions? All right, then let's move on. Today is a very basic kind of lesson. Every time I teach this lesson and I design this course, I kind of go, geez, do I really need to do this lesson? But it's in the textbook, and I think it gives us a good introduction to the concept of radical functions. We're not really learning that much new today. What you're learning today is what a particular function looks like. That's pretty much it. And then we're going to be transforming it. The particular function that we're talking about, everybody, is this one. You're going to be learning, what does the graph of f of x equals root x look like? What are its properties? Like, are there any x or y intercepts? What's the domain? What's the range? What's the shape? All of that. And ultimately, what we're going to end up doing is applying a, b, h, and k to that highlighted function to solve problems. But listen, if you know what any function looks like, you can apply a, b, h, and k to it. So the only new thing is this starting function. And to introduce this idea, We call these base functions in Math 30. Y equals x squared is a base function. It's something that everybody here should know the appearance of. It's a parabola with a particular width or height, with its vertex centered at the origin. When you go from the vertex over 1 in either direction, you go up 1, and when you go over 2 in either direction from the vertex, you go up 4. You have this basic shape, this base function. And you should be able to apply this to that. You should be able to, for example, if f of x is x squared, you should be able to say, what does that look like? And notice, by the way, what I wrote here, I'm going to take this opportunity to review something with you again. Notice that what I wrote here, this part, is that. If you look at the top left of the screen, it's f of x equals x squared. So when I write f of, by putting in values of a, b, h, and k, that f of part becomes squared. All right. Well, that's a base function. There are other base functions. And some of these we know about already and some we don't. You don't know what y equals x cubed looks like, but we'll talk about it in the next unit. You should be able to apply a, b, h, and k to that. In general, we will learn in the next unit that x to the 4 or x to the 5 or x to the 6 is a function that you should be familiar with its appearance so that you can apply a, b, h, and k to it. This is called an exponential function, and you don't know much, if anything, about that because we have a unit called exponential, and logarithmic functions, where we will learn about those. Absolute value function, you do actually know what this looks like because you learn about these in Math 20. That's that v with each side of the v at a 45-degree angle if the axes are scaled the same, with its vertex at the origin, and you can apply a, b, h, and k to that. We will learn about transforming this function and what that looks like. We will learn how to transform trigonometric functions because we have to, and we will first learn what they look like. What we're doing today is that. We're looking at what f of x equals root x looks like so we can transform it and answer questions relating to it. So, a radical function is any function where the independent variable, the x variable, is included as part of the radicand. I will remind you of something, that this whole thing is a radical, but what's under the radical sign is called a radicand. The radicand is the argument of a radical expression. What I'm telling you is a radical function is a function where x can be found under the radical sign. Okay, it's part of the radicand. So these are examples of radical functions. F of x equals root x, or y equals root x if you like. Y equals negative 1/2 multiplied by the square root of 2x minus 12, and then minus 8. Sometimes when I write things, and you might want to get in the habit of doing this if you're writing for a written response, I extend this a little bit and I drop a little overhang down just to indicate that that's where it ends. Because sometimes you have to look very carefully at where it lines up when it's done in print. Or y equals the square root of 2 times the square root of negative 4x plus 5. So as a warm-up, we want to investigate what y equals root x looks like. To begin with here, you need to make a note. Root x means the principal square root of x. When you see that square root symbol, it means the positive square root. Does anybody remember what I tell you in terms of when do you write plus or minus? Well, you use plus or minus if it says plus or minus, but you write plus or minus if you introduce the square root. So if you're rearranging an equation and you take the square root at some point, you have to say plus or minus. I hope you can see why I've chosen these values of x, because the principal square roots of those numbers are fairly basic. The square root of 1 is 1, root 4 is 2, root 9 is 3, root 16 is 4, root 25 is 5. And plotting those points is pretty simple. I'm not giving you a ruler today because this is not going to be a straight line graph. 0, comma, oh, and I don't have 0 in the table. Do I have 0 in there? I do. Good. I fixed it on yours, but not on mine. When x is 0, the square root of 0 is 0 as well. So we can plot a point at the origin. You can plot a point at 1, comma 1. We also have a point at 4, comma 2. And many of you right now should be starting to see that this is the same pattern as y equals x squared, but it's backwards. If you just stop what you're doing for a second and look up here, when I take a look at y equals x squared, which is not this, if my nose is the vertex, we go over 1 in either direction and up 1. Then we go over 2 and up 4. Then we go over 3 and up 9. This is going up 1 and over 1, up 2 and over 4, up 3 and over 9. And it doesn't go in both directions because it's only the positive square root. It's not plus or minus. So we can continue to plot these points. When x is 16, y is 4. When x is 25, y is 5. And the curve, you have to draw your best curve here. I don't think it's a test of your artistic ability. That would never happen on an exam. I shouldn't say that. Is it possible that you might be expected to graph this on an exam? Yes, but I think the markers and myself are reasonable in what to expect. If it looks like you've just kind of closed your eyes or drifted off and drawn some kind of curve, that's not good enough. It should try to pass through the points. If your hand is a little shaky because you're always caffeinated, that's fine. Okay? But it is a smooth curve. You can also look at this on your calculator, right? We could have just entered y equals root x on the calculator and set up the window settings to match this scale. But there's value in what we're doing with this in terms of what we'll do tomorrow. Well, not tomorrow, Monday. That's what it looks like. So identify the domain and range. Well, the domain is x is greater than or equal to 0, and the range is y is greater than or equal to 0. I mean, it starts at 0, 0, and it moves to the right, and it also moves up. Some people, and I don't think that there might not be anybody in the room who thinks this, but some people might look at the shape of this curve and think that it's kind of leveling off and it's never going to get up to a gajillion for y. It will get up to a gajillion for y. It will approach negative infinity for y. It's just going to happen very, very far down the road for x. All right. Now, I've got in the notes all radical functions can be written or expressed or created by transforming that base radical function y equals root x. I probably should have the word many. It's not all. All radical functions whose radicands are linear can be expressed or created from transformations of root x. But if you have the square root of something that contains quadratics, like the square root of x squared plus 3, that can't be. So technically it should say many. If you apply a f of b bracket x minus h plus k to f of x equals root x, you get this. And the reason, again, this is not something that everybody sees necessarily. But I hope, my hope is if I keep coming back to it, you will see it automatically. That this f of the brackets, if f of x is root x, then f of the brackets is root of what's inside the brackets. So when I write f of b bracket x minus h, that means I put b bracket x minus h in for x in f of x. But that means I put b bracket x minus h here, and that's why we have a square root sign there now. It's the square root of b bracket x minus h. And there's an a in front and there's a plus k at the end. So what we're talking about is transforming f of x equals root x to g of x equals this thing. And that's not on your formula sheet. This template is not on your formula sheet. But listen, if f of x were x squared, this would be y equals a b bracket x minus h squared plus k. That's not on your formula sheet. There are some that are on your formula sheet that we'll learn about later, but you should be capable of applying a, b, h, and k to this function on the left, f of x equals root x, to give you that. So, sketch the graph of each radical function using transformations of the most basic radical function, and then state the domain and range. I had to retype something because I had a corrupt file. Can you confirm that example 1a that I have typed up there is the same as what you have in your handout? Okay. Do me a favor, take a second and write down what the values of a, b, h, and k are by looking at the equation of that function. Remember that you always have to have it in the correct form. Y has to be by itself. Yeah, would you agree? Again, what you're doing is you're comparing this at the top of the screen to what I've written at the bottom of the screen, knowing that f is the square root. So a is the number in front of the function. The function is the square root, so a is 3. B is the number in front of the x, which is negative 1. Then we have in brackets x minus 5, so h is 5, and k is negative 1. I'm not going to write this down. I don't mean to belabor the written response concept, but if it were written response, you would clearly explain all of this. But you should know that we need to stretch this vertically by a factor of 3, because a is 3. You should know we need to horizontally reflect this across the y-axis, because b is negative 1. You should understand that since b is negative 1, there's no horizontal stretch, though. And then you need to realize that after you do that, vertically stretch it by a factor of 3 and reflect things horizontally, then you move things 5 to the right and 1 down. And all of those things would be items that you would explain or write down on a written response. So we're going to do this all in one shot. I'm going to take this point right here, which we can call a vertex. It is a vertex. And I'm going to stretch it vertically by a factor of 3. Done. I'm going to reflect it horizontally. Done. It doesn't move. It's invariant in terms of those. And that means that this point is going to be shifted 5 to the right and 1 down. Now here's an interesting observation. Since the vertex is not affected by a and b, the vertex will always be at h comma k. Much like last year, the vertex of a parabola was always at p comma q because the stretch didn't move it. The same thing goes here. So you can make an observation that this will always be h comma k. Let's continue. I take this next point. I'm going to start referring to some of these points as key points. I take this next key point on the original function and I stretch it vertically by a factor of 3. it was 1 away from the horizontal axis. So stretching it vertically by a factor of 3 will put it 3 away. I reflect it across the across the y-axis. It's a horizontal reflection. And then I shift it 5 to the right. 1, 2, 3, 4, 5, and 1 down. What this is telling me, and I don't want you to draw this yet because I want at least one more point to give more detail in my graph. What this is telling me is the transform function will look something like that, going up and to the left. Okay, but let's not draw it yet. Let's get another point in there so that we know exactly how steep it is. Like, I don't think I've done a good job here. So I do have another key point. Now, that other key point happens to be right underneath here. So there is a point that I've got with this red dot, which is a point on the new function, but the point below it is a key point on the original function. So on the original function, 4, 1 is a key point. I stretch it vertically by a factor of 3. That point was 2 away from the x-axis. Now it's going to be 3 times further away, which is 6. I reflect it across the x-axis. It's 4 away from the x-axis on the right, so it has to be 4 away on the left. And then I shift it 1, 2, 3, 4, 5 to the right and 1 down. And now at least I have a little bit more, I always say, I don't know why, I have more texture to my diagram. I have more information in it. So you want to do your best to sketch it. And again, I'm a little wobbly here. I don't expect anybody to be perfect when you sketch these. It's going to look approximately like that. With an arrow on the end in the top left. I just, in kind of glancing around the room, I see, and I don't know why a couple of you have done this, I see a couple of you have drawn in something down here. That's not, it doesn't exist. There's nothing there. This is only half of the inverse of x squared. It's only the top half because of the positive square root. What's the domain and range? Well, the domain is x is less than or equal to 5, and the range is y is greater than or equal to -1. The vertex is at 5, -1. This is at h, k, which will always be the case. This number will always be h, and this number will always be k if we transform root x. The domain, if I can go back for a second here and look at the domain, well, we don't need to. I have the graph here. If I look at the domain of this function that I started off with, it was x is greater than or equal to 0, and the range was y is greater than or equal to 0. Why is it that the range of the transformed function is still greater than or equal to, but the domain is less than or equal to? Anybody be able to tell me? Like, it makes sense. If y is greater than or equal to 0 and I shift the thing down 1, y will be greater than or equal to -1. That makes sense. Why, though, if I shift this blue graph 5 to the right, why doesn't the domain become or x is greater than or equal to 5? Because it was greater than or equal to 0. Will? Right, b is negative. So if b is negative, it's going to take that inequality on the domain and flip it. By the way, if A was negative, it would take the inequality on the range and flip it. So if you ever have one of these and you're told that y was less than or equal to some number, that tells you that A must be negative because it's been flipped vertically. All right, let's take a look at this one. I would like everybody to take a minute and write out what A, B, H, and K are equal to before we continue. Oh, okay. I was just going to say, do you want to think about that number a little bit more? I see what you did there. Well, I'm actually quite impressed that most people, I'm looking at this and you are getting H right. You're remembering that we have to factor that 2 out. So when I take that original function and I rewrite it, I can write 2, negative 2 square root, factor that 2 in front of the x out and be left with x plus 12. Sorry, be left with x plus 6 and then plus 3 afterwards. That means that A is negative 2, B is 2, H is negative 6, K is positive 3. Can we agree on those numbers? Okay, so what happens? A is negative 2. This graph needs to be stretched vertically by a factor of 2 and reflected vertically. B is 2. This graph also needs to be stretched horizontally by a factor of a half. And I'm going to choose to write that down. So this is a stretch by a factor of 1/2. It's the reciprocal of B. After we have reflected vertically, stretched horizontally, then we can worry about shifting everything 6 to the left and 3 up. This point has to land there, because we can memorize that H comma K is where the vertex is going to be. Or everybody, if we take this point and we reflect it vertically, it doesn't move. If we stretch it vertically by a factor of 2 now, it doesn't move. If we horizontally stretch it by a factor of a half, it doesn't move. All that remains is to shift this 6 to the left and 3 up. Let's move on to another key point. I'm going to reflect this point vertically. It goes here. I'm going to stretch it vertically by a factor of 2. It's going to be twice as far away from the x-axis now. I'm going to stretch it horizontally by a half, which will put it here. And now I need to move that 6 to the left and 3 up. 1, 2, 3, 4, 5, 6. 1, 2, 3. I think there might be some of you that would understand where this point lands in relation to this point based on the stretches and reflections. It lands below, that second point lands below the vertex because of the vertical reflection, but instead of it being a 1 kind of square between the 2 points, it becomes a 2 1/2 because of the vertical stretch. If you don't pick up on that, that's fine. Incidentally, you could do all of this with mapping, but it is a mess. You could apply mapping rules to these points. Moving on, let's just do one more point. Another key point is at 4, 2. What are we doing here? Let's stretch vertically by a factor of 2 first, and then reflect it. It doesn't matter. Now it's going to be 4 below. So even if I start here and I reflect it first and then stretch it vertically, it still ends up at this point. Now I'm going to stretch this horizontally by a factor of 1/2, and now I can go 6 to the left and 3 up. Answer the question.
Please return to the cosmetology map. Prentice Gist, please return to the cosmetology map.
So it's going to look like this. Domain x is greater than or equal to -6. Range y is less than or equal to +3. Vertex, we weren't asked for the vertex, but again, I want to point out that it's at -6, 3, which is h, k. Any questions with B? All right. Determine the equation of the function shown. This is fairly straightforward, but it doesn't have to be, and sometimes it won't be fairly straightforward. Okay? When we take a look at the original function, root x goes through these 3 key points. 0, 0, 1, 1, 4, 2. If you want, you can write those points in. I'm going to erase them in a second. If you want, you can actually put the original curve in. But it doesn't matter. What I know is that the relative position of the vertex and the first key point, the one that I identify as being 1, 1, that relative position is that 1, 1 is 1 above the vertex, and it's 1 to the right of the vertex. When we take a look at this graph, the first thing we notice is this graph doesn't go up and to the right. It goes down and to the right. If it goes down, that means that A must have a negative value. Has to have a negative value. Because the range has gone from being y is greater than or equal to something, and all of a sudden when you look at the range of this, y is less than or equal to something. And I was looking at this backwards in my mind. It also is not going to the right, it's going down and to the left, isn't it? And that means that instead of going to the right, since it's going to the left, B is also negative. Right. Now, how do we determine the values of A and B? Well, let's leave that alone for a second. Do you know the value of H and K? Definitely, because it's where the vertex is. Whatever A and B are doing doesn't move the vertex. A and B will not move this green point on the original function, and the green point ends up being that green point, which is shifted 7 to the right and 5 up. So we actually know that H is 7 and K is 5. Now the question is, how do you find A and B? Well, you can do it this way. The vertical distance between the vertex of the original graph and the first key point is 1. The vertical distance between the vertex of the transformed graph and the first key point is 4. Things are stretched vertically by a factor of 4. Does that make sense? The horizontal distance between the first key point and the vertex is also 1. This goes from 1 to 4. This goes from 1 to 3, which means the graph must be stretched horizontally by a factor of 3. And that means that B contains 1/3, and it's also negative because it's been reflected. All that remains is to put that series of parameters into this general template, and we get y equals a, which is negative 4, f of, what's the square root? F is the square root. B bracket x minus h, negative 1/3, x minus 7, plus k, which is 5. This ending of the brackets here is where the square root function ends. K is afterwards. Any questions with that example? Okay, now I'm going to do this question 2 more times, and I'm going to change it a little bit, because you're going to run into questions like this on exams and in your assignment where it doesn't seem to make sense. We are told, if I now repeat the question, and you have room, you can rewrite this A, B, H, and K down below. You can say option 2, if you like. What if I told you that A is negative 1? And right away, I can see the furrowed brows on your faces going, but A can't be negative 1 because that key point is 4 times further away, vertically. But there's nothing that says that this point here has to be this point after the transformation. It could be some other point. Some other point, due to a series of transformations, might have landed there. And again, this is not making sense to some of you right now, I can tell. You're saying, well, but that point is there. Just play along for a minute. If you're told A is negative 1, then what you have is a missing parameter. And you find a missing parameter by loading into the function an ordered pair. Well, what's the function? The function in this scenario is y equals negative 1 times the square root of b, which we don't know, times x minus 7, and then plus 5. And we have a missing parameter. And I've tried to, for those of you that had me in Math 20, I started back then. And if I taught Math 10C, I would do it there too. A missing parameter is always found by loading in an ordered pair. And the ordered pair here is 4, 1. 4, 1 is a point on the function that the function passes through. So I'm going to put in 1 for y, four for x, and I'm going to solve this for b. So the first thing I'm going to do is subtract 5 from both sides. When I subtract 5 from both sides, I'm going to show my work here, although part of me doesn't feel I need to, but I'm just going to show it. I end up with negative 4 equals negative 1 root b times negative 3. 4 minus 7 is negative 3. I'm going to divide both sides by negative 1. And again, I'm showing all these little steps, but I don't really think I need to. And I get 4 equals root of negative 3b. Now I'm going to square both sides. And divide both sides by negative 3. And I get negative 16/3 for b. Which means the function is y equals a f of b x minus 7 plus 5. Okay, let's try something now. So what this means, by the way, is the horizontal stretch factor is 3/16. Let's try something. Let's graph what we got here on our calculator. -4 square root -3 bracket x minus 7, close the brackets on x minus h and on the function, and then add 5. I'm going to choose to go zoom 6, zoom standard. There it is. By the way, we could confirm something. Did I enter that right? -4. Oh, no, I didn't enter it right. 1 divided by 3. Whoops. Divided by 3 bracket x minus 7 m bracket plus 5. That's better. I put 3 instead of a third. So when I take a look at this, this is what it looks like. Let's check something out. If I go trace 4, it goes through 4, 1. Okay. Now I'm going to graph this function. It's on the bottom left of the screen. I'm going to leave the other one on. I have -1 times the square root of -16 over 3 multiplied by x minus 7, close brackets on the x minus h, close brackets on the function, plus 5. Now, if I'm claiming these are the same, you're not going to see anything. Let me double check that I've entered it correctly. It looks okay. I'm going to go over to the equal sign, or past the equal sign. I don't know if you've ever played around with this, but if you hit enter, you can graph things using different visuals. I like the little bouncy ball. This is going to show me a ball that moves along the function. So when I go graph, it's the same function. So before I go on, I want to point out to you, and I'm going to put this function, which I will highlight. No, I'm going to do this instead. I have on the left-hand side, it's a little small, but I have on the left-hand side what we got when we did it using a key point and 2 stretches. And I have on the right-hand side doing it this way because I was told, no, a is -1. What this is saying is there is a vertical stretch by a factor of 4 and a horizontal stretch by a factor of 3. Would you agree? Among other things, reflections and translations. What this is saying is there is only a horizontal stretch by a factor of 3/16. Would you agree? Because b is 16 over 3. There's also a horizontal reflection. So now we've elevated things to a Math 30-1 diploma exam level, because what you need to understand is there's 2 different ways to get that graph. And you could literally be given a question where you're given this graph, and maybe it's a numerical response question, and you have vertical stretches and horizontal stretches and all of these options, and you're told one way to achieve the graph is to use which 2 pairs of stretch factors, and a different way can be using which other 2 stretch factors. And there's a third possibility. In fact, there are an infinite number. But there is a third possibility here. And I don't think you really need to write this down. But if I said, you know what? No. B is -1. What's the vertical stretch factor then? Or what's the vertical parameter A? Well, your equation would be this. Y equals A, which is unknown, root -1 x minus 7 end root plus 5. Does that clock with you? Does that make sense? So how do we find this missing parameter? You load in four comma 1. So I get 1 equals A root 3 plus 5. 4 minus 7 is -3 times the -1 is 3. I subtract 4 or 5 from both sides and get -4 equals A root 3. And that means that A is equal to -4 over root 3. My function is this. If I graph that, it should be the same graph again. So I am going to put in -4 divided by the square root of 3. I got to close the brackets on that square root. Multiplied now by the square root of -1 times in brackets x minus 7. Close the brackets on the x minus h. Close the brackets on the function, plus 5. And what can I do here? Let's make this thick. I want to double check to make sure I've entered it correctly. I know on my calculator it doesn't really look like it's divided by root 3, but it is. Looks okay. And I'm going to quit out of here. I'm going to clear draw so that it starts from the beginning and graphs all three. Okay. If I graph now, here's the first one, here's the second one. It's a little slower with the bouncy ball. And there's the third one. Now I want to kind of put a bow on this and write all three down together so you can look at the equations. The first one we got was y equals -4 root -1/3 x minus 7 end bracket end function plus k. The second one we got was y equals -1 root -16/3 x minus 7 end brackets on the x minus h, end brackets on the function plus 5. And I'm going to ask you to look at these three things I'm highlighting. My highlighter is dead. I'm going to ask you to look, I'll risk it, at these three things I'm highlighting, which are the only things that are different in these functions. Everything else is the same. And ask if you can see how what I've highlighted is in fact the same set of numbers for both. One of the things you learn, and this is last year in 20-1, and you also do this a bit in 10C, is if you have something like the square root of a times b, I can write the square root of a times the square root of b. That's why you're able to take something like root 18 and say it's 3 root 2. Remember doing that? Okay. Well, this 16 is being multiplied by the x minus 7, and it's being multiplied by the negative 1/3. So I can take the square root of that 16 and extract it. And it's going to end up being a 4, which joins forces with the negative 1 to become negative 4. On the other hand, if I look at this 3 here, if I want to put this 3 on the left hand of the screen back under the square root, I have to square it. So if I look at taking this 4 right here, and I pack it back under the square root, it's going to become 16, and it will become 16/3. Or, if when I take the 16 out, it becomes 4, then when I take the 3 out, it becomes the square root of 3. And that's why it can be written as negative 4 over root 3. And I will finish this by saying, you could be told any value of a here. You could be told a is negative 3. Now, you can't be told any value of a because a must be negative, right? It won't work if it's not negative. If it's not negative, probably you're going to end up taking the square root of a negative somewhere. It just won't work. But there will be a magical value of b that if a is negative 3 will create the same graph. And that's our first foray into the idea that you can have an original and a transformed graph, and there might be many ways to get it. All right, one last example. This is a fairly quick one. Write the equation of the radical function resulting if we take y equals root x and we reflect it horizontally in the y-axis. We stretch it horizontally by a factor of 3. We also stretch it vertically by a factor of 1/2, and then we do a couple of shifts. Do me a favor, please. This time using the words describing what's happening, write out the values of a, b, h, and k. Sometimes I need to talk my way through this. I wrote down my answers, but I'm going to talk my way through it just to make sure that I didn't make any mistakes. We have a horizontal reflection. It's across the y-axis, as are all horizontal reflections in this course. But if it's a horizontal reflection, b is negative. If it's stretched horizontally by a factor of 3, that's the stretch factor. B is the reciprocal of that, which is 1/3. It's also stretched vertically by a factor of 1/2. The vertical stretch factor is always a, the absolute value of a, but there's no vertical reflection, so a is 1/2. And then 5 units up means k is 5, and 4 units left means h is negative 4. We can live with that? Okay. So I'm going to write this equation down again, although it should be second nature to you. You should be intimately connected to this, like you know it. So y is equal to, and I just do stuff left to right. We've done this a lot, but it doesn't hurt to do it again. A f of b bracket x minus h. Well, b bracket x minus h is this. F of, it's a square root function. And that's where the function ends. The function part of the transformed equation ends there. I mean, the whole thing is a function, but I'm saying this part dealing with the b and the h ends there. Then we go plus k, which is 5, and we're done. Any questions with that final example? Listen, if it's a, well, I'll give you a numerical response situation. you're told that y is equal to 1/2 root negative, no, yeah, negative 1/3 x minus c plus 5, and asked for the value of c in decimal form. C is not -4. C is not even 4. This has been expanded out, and if you expand this out, you get that. So the answer would be whatever 4/3 is, 1.33. Right, on page 72, there are some questions, and then, as usual, some multiple choice numerical response style questions for you to practice. I remember being a student in Teachers Convention was amazing way to start the semester. But I also remember waking up in a cold sweat after going to bed on Sunday night going, oh, I forgot about this, I forgot about that. Just keep track of stuff, right? Take your math home. I would recommend spending some time doing that written response so that if you do have any questions that you might need a little guidance with on Monday, the day before it's due, you can ask me Monday. But if you leave it till Monday night, you might be in the dark there. Okay, so get to work. I'm going to be around to help you out in just a minute.